Hello, business analytics superstars, and welcome to Chapter 14, Multiple Regression. If you've ever wondered what drives sales, whether it's price, marketing spend, brand image, or perhaps a mix of other factors, then multiple regression is your key to unraveling that complexity. In real life, outcomes are rarely influenced by just one factor, and hence multiple regression helps us account for the numerous variables that contribute to business performance. Now, in simple linear regression, we modeled the relationship between a dependent variable, such as sales, and just one independent variable, such as price. Multiple regression, however, allows us to include several independent variables: price, marketing spend, brand image, competitor actions, economic conditions, and much, much more. The idea is to build a model that better reflects the full range of factors influencing our outcome of interest. Hence, the beauty of multiple regression is its ability to account for multiple influences on the dependent variable simultaneously, offering a more complete picture of the relationships at play. Now, when we add multiple independent variables, each coefficient tells us the relationship between that variable and the dependent variable while holding all the other variables constant. For example, in a sales model, the coefficient for price would tell us by how much sales would change if we were to adjust the price by 1 unit, assuming that factors like marketing spend and brand image remain unchanged, i.e. constant. This ceteris paribus approach, where we isolate the effect of one variable while holding others constant, helps us make sense of the individual contributions each factor makes to the outcome. As before, R squared measures the proportion of the variation in the dependent variable that is explained by the independent variables. In other words, it tells us how well our model fits the data. The higher the R squared, the better the model explains the variation in the outcome. However, when we add more independent variables to a model, the R squared tends to increase, even if those variables don't actually improve the model. Now, that's where adjusted R squared comes in. Adjusted R squared penalizes the model for including irrelevant variables, making it a better metric for comparing the fit of different multiple regression models with different numbers of predictor variables. It helps answer the critical question: is our model getting more accurate or just more complicated? Now, with great power comes great responsibility. One of the biggest challenges in multiple regression is multicollinearity, quite a mouthful. That is when two or more independent variables are highly correlated with each other. For example, imagine trying to use both price and discounts as independent variables to explain sales. Well, since price and discounts are pretty closely related, multicollinearity could make it rather difficult to estimate their individual effects accurately. The presence of multicollinearity inflates the standard errors of the coefficients, making it harder to assess their statistical significance. As a result, we need to be cautious when interpreting the results of a multiple regression model and consider removing or possibly combining variables if multicollinearity becomes an issue. Now, unlike simple regression, which typically deals with quantitative data, multiple regression can actually handle categorical variables, variables that take on a limited number of categories, such as gender or region. Here, we use dummy variables to represent these categories numerically, allowing us to include them in our regression model. For instance, if we wanted to see how sales differ across regions, we'd use dummy variables to code each region as either 0 or 1, although we have to reserve one region to be the reference category to avoid multicollinearity. In addition to including multiple variables, multiple regression also allows us to explore interactions between variables. For example, the effectiveness of marketing spend on sales might itself depend on the media channel used. So including interaction terms in the model helps us capture these more complex relationships. While multiple regression is powerful, its accuracy does depend on selecting the right variables. If we leave out important predictors, what's known as omitted variable bias or OVB, our model could give misleading results. For instance, imagine trying to predict sales using only price and marketing spend, but forgetting to include seasonality. By leaving out seasonality, our model may incorrectly attribute changes in sales to price or marketing rather than the actual reason, i.e. the time of year. This is why model building is an essential part of multiple regression. We need to ensure that we're including all relevant variables while avoiding overcomplicating the model by throwing in too many irrelevant ones. Model selection techniques such as stepwise regression can help in this process by systematically adding or removing variables based on their statistical significance. Multiple regression has broad applications in the business world. One common use is in marketing mix modeling, where we aim to understand the impact of different marketing channels on sales. We might use variables like television ads, digital marketing spend, price, and competitor actions to model how these factors collectively influence sales. The insights gained can then inform better allocation of marketing budgets, say. Another application is in finance, where analysts can use multiple regression to model stock returns. By incorporating factors like market risk, interest rates, and company earnings, we can assess which variables are most important for predicting future returns. So, superstars, are you ready? On your marks, get set, regress.